Okay, this is part 2 of the next day, and also the second screen recording that I'm making of programming of Rehearsal Pro. Here's the actual app running in the simulator. This is an iPhone 12 simulator, which the other video didn't show at all because it's focused entirely on the development and the code. So that first video was the first one, part 1, and we talked about a lot of stuff. I talked about a lot of stuff. And it was probably pretty boring to anyone watching it, if anybody's watched it or going to watch it. But going back to it, it may turn out to be incredibly helpful to me because I kind of had a revelation after thinking it through, both while I was talking through the recording and thinking about it a lot today. And that's the issue of really unnecessary work and complexity. So where to start? I think the key point was when I was saying that we have this data representation for line sets, and it literally has 4 different representations in the app given the new approach. If we're going to use the SQLite to store, to persist this information in the local database on the app, that begins with an SQL declaration. So that's one representation of the data. That's not the actual way the data is stored in the database, that's the way it's accessed. But we think about it as this is the representation. These are the types, these are the names, this is how it's organized, this is how it's accessed, this is how it's updated, this is the CRUD for that data. And then SQLite automatically is going to convert this to a Kotlin data class. Kotlin Multiplatform is going to, or does, convert it into an Object-C interface. So we have, at a minimum, 3 representations of this information. But there's a 4th representation. And that 4th representation is the actual JSON that comes from the back end. And that back end is doing really nothing more than persisting this state. There's a few other services the back end provides, but for the most part, it's just durable persistence of this information, what a line set is. So it's really not a lot different than a local database, because the database is persisting durably that state locally. And storing it remotely allows it to be distributed to other devices for the same user's account, as well as providing a backup, but it has to be synchronized. And replication synchronization of replicated state, replicated data is one of the most difficult and challenging things in software development. Music's a little loud, bring that down. So we're looking at 4 different representations of essentially the same information. Why is that even necessary? And I began to realize one of my philosophies, both in life and in development, is to be willing, and not just willing, but also to constantly challenge assumptions. And that includes the most fundamental, implicit, built-in, unconscious assumptions, which I didn't even do here, because I was realizing, why are there 4 representations of the same information? Is this necessary? Maybe it isn't. So the one thing that's a given, no matter what I do on the front end to rebuild the app, design the app, rewrite the app, leave it the same, the back end is going to stay the same. I'm not touching the back end. I'm not touching the means of communication to the back end. And that means of communication is HTTP REST calls to the persistence provided by the back end, transferring the information via JSON. All of the information being stored locally is also stored remotely. So there isn't anything that's missing from the back end. So that means all the JSON that comes from the back end provides all the information. Why not just keep it in JSON? Why does it need to be converted to a local relational database? For that matter, why does it even need to be converted to an in-memory object? Whether that's a data structure or a data class resembling a data structure, an Objective-C object, or even a Swift struct. Why? Why not keep it as JSON? It may seem naive, but when we think about it, this information itself in this particular app, the purpose of this app is to allow actors to store scripts, work with their scripts, modify them, share them, practice scenes, create line sets. The bulk of the data here that's actually managed by the app is binary. It's PDF files for the scripts, and it's audio, and it's video. So you can capture video files, you can capture audio. So the bulk of the data is binary data anyway. It's not stored in the database. These are stored as files locally and remotely as the original binary files that they are: PDF files, audio files, video files. The stuff in the database is informational. It's effectively metadata. As you can see, it's mostly strings and dates. This is not heavyweight data, and there's not a lot of it. If a user has 1,000 scripts, if a user has 10,000 scripts, right, or 100,000 line sets, this is not a lot of information. They're not going to be generating reports or doing searches across thousands of instances of these things, right? They're going to be using them one at a time. Open a script, set of line sets, maybe a couple dozen line sets, maybe 20, maybe 100. That's not a lot. And at the power and speed of modern devices, even the lowest end iPhones are faster than servers used to be. So this assumption that it needs to be converted into an in-memory binary object for ostensibly performance, speed of access, right? Because parsing strings, parsing JSON, searching for names, searching for attributes, searching for labels and properties is slow. Well, it's really not that slow when you think about it. The JSON coming from the back end has to be parsed anyway. Every time they log in, it tries to synchronize with the back end and see that, are there changes locally that need to be replicated remotely? Are there changes remotely that need to be replicated locally? That's the synchronization part. And that's going to be moving JSON back and forth across the wire, parsing it, converting it, storing it. Why convert it and store it? Why not just keep the JSON intact? Right, that literally is the simplest approach, right? The one thing that is a given is that the backend is going to be providing this information through JSON. Not going to rewrite the communication with the backend, not rewriting the backend, just the front end. So going through all this rigmarole to parse it, convert it into memory objects, whether that's Kotlin or Objective-C, and then store it in a local database, what's the point? Obviously, the point is performance, but is this a performance issue? This is premature optimization. Not even really premature, it's kind of assumed the way things are done, and I kind of fell into this trap as well. Remember, the original project uses core data. So the original project deals with at least 3 representations, right? It doesn't have Kotlin. And I'm going to discuss that in a minute. I'm going to talk about complexity when it comes to this approach with Kotlin Multiplatform. So the original approach doesn't have at least the programmer doesn't create this SQL representation. This is being done for us by core data. So if we go back to the legacy code, we look at the legacy code for line set, core data class, right? So we've got this class declaration. Properties that actually matter to us are in here. And there's all this other miscellaneous extension functions here. But for the most part, this is all we care about, right? This is the informational stuff. This is the domain. This is what's relevant. And again, this isn't even the bulk of the data, right? This is metadata accompanying a line set is really made up of audio files. That's not even in here. The audio files themselves are stored locally as individual files simply in the local file system, not even in the database. So the database is really just serving as persistence for this metadata. So before I came along, the original code is using core data. Programmer declares this interface. Core data is doing what it does. This is an ORM, right? So this is the object representation as Objective-C. Core data acts as an ORM, generates whatever SQL or schema stuff it needs to talk to SQLite. It's using SQLite built into iOS. So if I were to add SQLite, I'm not changing the underlying persistence mechanism on the iOS side. I'm adding one on the Android side, making use of that because Android doesn't have any persistence yet. It hasn't been written. So it seemed to make sense, right? We're going to, this technology is already being used on the iOS side. It's the standard approach. Core data is the default. If you build any app, any iOS app from Apple, they're going to say stored in core data. They have a new thing coming out, which is Swift data, which is probably just a new type of mapper that's going to map things in a more friendly way. I'm making assumptions. I haven't actually looked into it. But I'd be surprised if it's not sitting on top of core data in the same way that Swift UI sits on top of UIKit, and is simply a friendlier way to ultimately store the stuff in SQLite. So that's the standard approach. And again, if you build an app that needs to persist information, what's the default? The default is going to be, well, of course, use core data, which is this black box around SQLite. And in the case of Kotlin Multiplatform, SQLite is a wider box, a grayer box. We're not really hiding the SQL, we're just making it more easy in terms of the object relational mapper part, which is, arguably thinner, right, in this case. You're in control of the SQL, and it's doing this. But why do we even need to do that? Let's back up even further. Let's challenge another assumption. Why do we even need data? Why do we even need persistence? That's the ultimate question. What the hell is persistence? Ultimately, all we have is information. This information in the app, when the user creates it, modifies it, edits it, looks at it, is data in memory. Why do we have to persist it? Because memory, transient memory, or memory, which is transient state, is not durable, right? In the absence of power, that state goes away. If you had an infinite guaranteed battery power to your memory at all time, which is essentially effectively what an SSD is, although that's magnetic, there would be no disk storage. There would be no need for disk storage. Or you could argue that the size of memory isn't enough, right? The amount of memory on a device in the massive amounts of gigabytes these days isn't enough to contain everything. So it's a smaller window over the entire set of state that is of interest. So larger storage devices are needed. But ultimately, let's say that's not the case. Let's just say there's plenty of memory, but person turns off the phone, app gets deleted, whatever reason. We want that state to be persisted, right? Now, persisting it in a local database on the phone, well, that persistence can be damaged in the same way that memory can be damaged. So it's a little more durable. The only difference is without power, the state is retained. Funny use of the word here. And then it's retrieved from the data store. But for the most part, the back end also is persistence. It's a distribution of persistence. It's a remote guaranteed, we still have your data just in case something happens to your app and your phone and you lose it. So why do we even need the local storage? We could just connect over the internet. In fact, the way the app nominally works, and this is one of the new features that I added, was you couldn't actually use the app unless you were connected online to your account. Now it's secured. One of the features we added was an offline feature, so that if you lost internet connection, you could still work with your scripts. You can't synchronize, you can't access the store, things like that, but you could work with your scripts, you could work with your scenes. So imagine somebody's, on a set somewhere and they lose their connection for whatever reason. They're in a room with, thick walls or that sort of thing. Previously, they would have lost their ability to actually read their script and work on their script. Now they can do that. We now have that feature. So being able to store locally is important. But assuming we didn't, let's say you have an app in which local storage is irrelevant. In fact, I previously worked on an Android app that was exactly that. It had no local persistence because of the concern about private data issues. It was a medical app. So there was a lot of constraints around that. And the information was only available transiently in memory once they connected to their account remotely. And when they disconnected, logged out of their account, turned their phone off, it was never there, which is by design not wanted. We could do the same thing with rehearsal. So in effect, the back end is your database, is your persistence. And if we go back to the pre-internet days, that was really the exact purpose of backends, right? We go all the way back to, we're so used to today thinking of, remote services sitting somewhere available through the internet, access via HTTP and REST services, right? Whatever they are. But there was a time when the internet was not the networking used, and when they wanted to distribute information systems, they weren't necessarily distributed worldwide, but like within large organizations, the strategy for that was distributed relational database technology. In fact, that was the purpose of a relational database, was built on the idea that the data is the most valuable, important thing. The applications come and go, but the data, the information about us, about our customers, or about our accounts, or if you're a bank, about people's money, that is the valuable asset that needs to be protected, preserved, and accessed in a large number of ways. And that's one of the reasons why database, the idea of a database, I'm kind of stumbling over my words here, but distribution of state was managed in that way. When client-server applications were created, this is pre-internet, we're still talking about like fat clients, they would basically connect to these databases remotely. So the whole purpose of it really was distributed persistence. Yeah, of course, there were remote procedure calls and there were runtime services and things that were more behavioral, but for the most part, most of the behavior is in the client application. But more than that, the data is accessed by a lot of different means, right? Spreadsheets, report generation, different groups, different interests, and that's why database administrators, the data centers of companies, were kind of their own little fiefdoms. They were basically the core around which all application development orbited and applications were used. Really, the center of IT was and is to some degree the world of these databases and the management of these databases and the availability of these databases, primarily being relational. That's been replaced by a host of REST-based services, which are for the most part just kind of front ends to some kind of data store. Now you don't know that it's a relational data store. You don't really know what it is. From your standpoint, it is the way this works, which is JSON instead of SQL is now your means of access. But for the most part, the purpose here, again, is the same problem. It's persistence. Just I want this stuff to be saved somewhere so that it's backed up when something happens to my device or it gets wiped out or I change phones. And also, I can access it from my other devices, right? A centralized location through which my state is managed. It's secured. It's only accessible by me. It has all those guarantees, but it's distributed. The point is it's distributed. And now we're not distributing via SQL. This very SQL was the means of distribution pre the internet age, one of the means of distribution, right? An application would make a remote SQL select to a database. So all the distribution was database distribution technology. This has been replaced by JSON. So why is it that it makes sense to persist it in a distributed fashion using JSON, convert the JSON to this object representation, then map this object representation into a local relational database? This local relational database for the purpose, and this is why context matters. This is why just the assumption of, well, just store stuff in core data, just store it in SQLite. It's important to question even the most obvious default. We don't even have to think about sorts of assumptions. It's not a good fit here because This is not a database in the sense of the information within is ever going to be accessed by anything other than the code within this app. It is literally local persistent storage, local durable storage of state, so that it's available to the application when the application is not online. That's it. That's its only purpose. So the flexibility that you gain from having it in a relational database, which is data access through standardized mechanisms that can make SQL calls and do selects and complex queries. We're not doing complex queries here. This is not a deep information database, a deep base of information where there's a lot of important connections between data, and we're going to be doing, for example, statistical analysis or demographics or something like that. I mean, for the most part, each user is going to have a set of scripts. Sure, it could be 1,000 scripts. Sure, there could be 100 line sets per script. But they're not going to be doing, we don't have this functionality that says, find this word across the entire database that might be in line sets, in scenes, and in scripts, and do a select and pull all these occurrences up. No, it's going to be open my script. Okay, I'm now looking at that script. Open my line sets. Oh, okay, now I'm looking at that line set. Open my scene. Okay, now I'm looking at that scene. It's simply retrieval. It's just direct retrieval, direct relationships. This script, this thing. So I'm getting kind of long-winded here, but I'm kind of building the case for myself. You realize, look at all this added complexity, all this added work, and it's probably unnecessary. So I'm going to shift gears here. I'm going to drop the SQLite thing for the meantime. I'm going to keep the branch in place. I can always come back to it and pick up the ball and run with it if we really decide to do that. But it seems really unnecessary. It's adding, well, is it adding complexity or is it replacing complexity? I would say it adds a little bit of complexity. Again, the existing app here already uses core data. Now, core data is hiding the fact that it's an SQL relational database from us. But in doing so, it's mapping it. So the iOS side is mostly dealing with two representations. It's got the Objective-C representation. Again, I don't know why I'm looking at the KMP one. It's looking at this representation, and it's looking at the JSON representation, which I guess I could pull. I mean, here we can see it here, line set JSON. So somewhere in here, it's really just a lot of the same names for the most part, most likely. I haven't really taken a look at all this here. But so it really just has these two representations. Now let's talk about complexity. The goal when I came on board was to take over maintenance of the iOS version as well as create a new Android version of this app. And the most direct approach, since the iOS app already exists, would be to simply write a new Android app, straight up native Android, using all the default frameworks provided by Google, written in Kotlin, that has exactly the same functionality as the iOS version. So, what does that do from a complexity standpoint? Does that add complexity? Well, it certainly does, right? So for now we have one platform, iOS, so we have to understand that and think about it. We have two programming languages over here that the app is written in, Objective-C and Swift. So that's a given. Now we're adding a new platform. We're adding a new language, a new API. The backend's the same services on the back end, but yeah, increases the complexity. There's no getting around that, right? In theory, we could use a multi-platform framework such as Flutter or React Native. And what would that do? That would mean ostensibly starting from scratch, re-implementing iOS, and this is why it doesn't make a lot of sense. We have an existing iOS app that's been around, very successful, very feature-rich. Why throw it out? Why rewrite it, right? That just doesn't even make a lot of sense. And we wouldn't disable this anyway during the process of building the new version if we were to rewrite it from scratch. So this would continue to exist for many years. But what would that do to the complexity of the development approach? Okay, one language, React Native, JavaScript. A new API, React. A new framework, React. You still have the two platforms. There's a little bit of insulation from the platform. You're not using the APIs directly. You're not calling UIKit directly. You're not calling the Android Vue frameworks directly. But they're still there. They still have to be debugged, diagnosed, dealt with. And of course, there's always the edges. This is a fairly sophisticated app in that it manipulates PDFs. It allows for annotations. It captures audio, video. It uses the devices. The microphones involved. So there's even a question as to how good a do it all in one platform technology will work. There's a lot of issues on the Flutter side. But let's say we went with Flutter React Native. What would it simplify? It would replace potentially 3 programming languages with 1. So is that a simplification? Sure. It's less cognitive load, right? And ostensibly, most of the logic of the app, let's say, for argument's sake, 80%, even 90%, would be written once. Is that a reduction in complexity? It's a reduction in redundancy. And I don't know that it's the same thing. I'm going to address that in a minute when we talk about Kotlin Multiplatform. But that would mean throwing this out or rewriting it from scratch. So that doesn't seem like the wisest approach in this case. So then the straightforward approach is just mirror this. Just mirror this in Android, write a new app entirely in Kotlin, use these straight Android frameworks, Jetpack Compose, use all the latest stuff, use all the recommended things, and duplicate what's been done. Kotlin Multiplatform is an alternative approach to that, to completely separate native. So what do we get the complexity of the platform in the different language, but we also get the redundancy. Every bit of programming logic in here is duplicated. Whatever currently exists in iOS and Swift is going to be rewritten in Kotlin. So the Kotlin Multiplatform proposition is to say a lot of that logic the redundancy can be eliminated. Now, it's going to be redundant in the sense of it already exists, right? This is not a new app, it's an existing app. So even if I write Kotlin code over here that can be reshared, that code, it doesn't eliminate the redundancy right away until the old code is replaced. So until the Objective-C and Swift code is replaced by the new Kotlin code. So it reduces ultimately the redundancy that would exist if I were to build an entirely new app in Kotlin only, not using multi-platform, not sharing the logic on the Kotlin side with the iOS side. But the iOS side already exists. So what's the problem with redundancy? Well, the problem is maintenance, right? Long-term maintenance, having to maintain two sets of source and having to mentally compare and make sure the logic matches. Whereas using the same set of source, if there's a bug on Android, the bug should also exist on iOS. If the bug is on iOS, it should also exist on Android. So it deals with the inconsistency problem. So redundancy, what's the problem with redundancy? It's inconsistency. Not only is it double the work, any changes made to Kotlin have to also be made, but then you expose yourself to greater vulnerabilities of things being wrong, of having bugs because of the difference, because they're not exactly the same. So at least if you can do it all in one language, again, this same proposition, the same thing that's gained by the proposition of using a React Native or Flutter or some other single language multi-platform technology. Kotlin Multiplatform originally was basically saying, yeah, we're going to be like those others. We're going to allow you to use Kotlin for both sides of the equation, for Android and iOS, but not all the way to the UI. Well, now that's changed, of course. So now Jetpack Compose, there is a Compose multi-platform. So they are pretty much targeting being a direct competition to Flutter and a direct competition to React Native. there's some nuances that are different between the three. Kotlin Multiplatform, let's assume the future Kotlin Multiplatform, where you can rewrite everything, including the UI. So you could actually do iOS UI using Jetpack Compose Multiplatform. You run into the same problems that you get from a React Native or a Flutter. Actually, Flutter is the worst case, because both React Native and Kotlin Multiplatform will actually just provide a common abstraction down to calls made to the native frameworks. In the case of iOS, it's UIKit. In the case of Android, it's the Activity View Framework, whatever we want to call it. Flutter actually bypasses both of those. It does direct rendering to a canvas. So it basically emulates and simulates the UI behavior, the UI framework code on iOS, and the same thing on Android. So not even considering that as a factor. Why do I talk about all this? Because this adds complexity. This actually adds more complexity than writing just the Android side in pure Kotlin and not bringing any of that over to iOS, leaving iOS exactly the way it is. Because what are doing, we can see that complexity, right? We see the bridging that has to happen. Right? We've got these platform functions. We've got this generated file that takes the Kotlin, becomes Objective-C, and because this is being done incrementally, there's an integration between Objective-C code and the Kotlinized Objective-C code, and the Swift code and the Kotlinized Objective-C code. That makes it more complex. So we're already, just the choice of using Kotlin Multiplatform actually is increasing the complexity from a cognitive standpoint of all the different kinds of technologies and the sort of issues and impedances that can come from that, above just doing a straight nothing but native Android by itself and not bringing any of that over to the iOS side. So what it's basically saying is, look, I'm going to increase your complexity, which it clearly is. This is more complicated. But I'm going to pay for that by reducing the redundancy that you would get otherwise. If you just do complete silos of Android and iOS, you're going to have redundancy. You're going to have double the maintenance of the same feature sets. You're going to have potential inconsistent behavior between feature sets. And this mitigates that. But you pay the price of this complexity, of this impedance between the Kotlin world and the Objective-C Swift world. And another philosophy that I have, particularly in programming, more than ever, is to do everything we can to reduce complexity. Reduce, less. Because complexity just automatically increases. It's like entropy, really. It almost is a force of nature in software. Every line of code that we add increases. It either increases one of two things. It either increases complexity or increases redundancy, right? I mean, if you think about it, even if you add a new feature that didn't exist before, well, is that redundant? Well, the feature didn't exist before, but sure, you're writing code that given enough time, you could refactor common behavior out of that with other code. So there's an inherent redundancy. If you make that feature and that code work just like another feature, okay, so it's not more complicated because it looks, one web page looks like another web page. But if they really look very much identical, then you've got redundancy. If they're not redundant, then they're not the same. Therefore, you've increased complexity, right? So there's no free lunch. For every line of code, for every feature, for every capability, for every enhancement we do to software, which is all that we do as programmers, right? We're starting from a blank slate at some point, and we're filling that slate up. We're adding things to it. We're creating this information systems, games, whatever it is. We're adding features, we're adding capabilities. So we're always either adding redundancy or complexity. We're either duplicating something almost the same as we did before, so redundancy, we're just more of the same, or it's different enough that now it's because it's different, the overall system complexity has increased. This just happens with everything we do. The only time we take it away is when we are literally taking it away, refactoring, reducing, removing, right? Getting rid of a feature, getting rid of a technology we don't need, subtracting. And think about it as programming. How much time do we spend actually subtracting versus adding? Most of it's spent adding. And the pressure from the commerce side of the world that pays the bills is the pressure is add, increase, add, increase, right? In fact, whenever we push back and we say, we need to subtract right now, the question is why? What is the business gain? What do I gain? What is the payer of the paycheck gain? Well, you're gaining you're gaining the benefit of reducing the likelihood. I mean, this is just a terrible way of saying it, but you're getting the benefit of this thing surviving. Let's put it that way. Because if we just continue to add and continue to add, you get the classic big ball of mud, house of cards, giant brittle monolith. You know, we've got all these metaphors that we use, and this is where all software ends up eventually. It ends up in one of two places. It either ends up not used, and so in the graveyard, in the Google graveyard, or it gets too big to be manageable, and then it typically gets abandoned, rewritten. And so the idea is all these different approaches, like how do we make this thing manageable, continue to serve our needs without getting out of control. And every line of code, every feature we add makes that challenging. So we have to push back and say, look, we need to reduce. We need to bring this thing back to a manageable level. It's getting to the point where it's unmanageable. And we can talk about velocity, right? Our ability to add new features slows. It's very fast in the beginning. That's why trying to judge software development based on the prototype phase or the startup phase or the building something from scratch phase is a really bad measurement, because things can happen very quickly in the beginning. And then as the system gets bigger and larger, it gets slower and slower and slower and slower and slower. And that's when throw out and start over again, the classic problem. We don't want to do that here. This is a good, solid working app. It works well, has a lot of benefit. Users are very happy with it. We're not going to throw this out. So to continue to manage it, we need to rein in. We need to continue to rein in any new features that we add to keep the complexity manageable. The only way that's doable is by subtracting, right? Subtracting can happen a lot in refactoring. Refactoring is identifying redundancies and reducing the redundancy. Now, reducing redundancy, again, doesn't reduce complexity, right? If I've got the duplication of the same thing, right? If there's code for this window and code for this window and it's copy pasted, but there's a lot of elements that are the same. They both have titles, they both scroll, they both do these sorts of things. That can be commonalized. So it can reduce the redundancy, but the feature is still there. The scrolling, the display, we haven't removed its capability. So whatever complexity is needed to support the capability is still there. So we can reduce something. How do we get rid of complexity? Well, we can't get rid of the inherent complexity of the app itself without changing the way it works, without changing its UX, right? Its user experience, its user interface, its outward design. So it's just complicated. The app is as complicated to the user as it is designed, which is fine. That's complexity. It's not too complex from the way it's designed. But a lot of the complexity we deal with as programmers is all the complexity underneath to make that work. That we do have control over. And this is an example of that. This is an example of just an inherited, in my view, unnecessary complexity, right? I've already said, we know we have to persist this state. We've got scripts, we've got line sets, we've got scenes. That's got to be persisted. Right now, it's already persisted on the back end. So technically, we could get rid of the local database entirely, and we would lose this new feature of being able to work offline, but we basically say every time you log in, it's going to communicate with the back end, it's going to get the state from the back end, and it's going to bring it locally. Now, we're not doing any performance analysis of that right now, but I can, in my mind, imagine, okay, bringing down line sets. Let's say you bring down 1,000 line sets from the back end. Okay, that's a pretty good amount of communication, but doable. But all the scripts, well, the scripts are, these are all PDFs. These are sitting in the cloud. That's what these cloud icons indicate. These are big. These are big binary files. Some of them contain audio. Some of them contain video. And that's a lot of information to bring down every time the user starts up the app. So yes, it is a performance optimization to store stuff locally. But it's clearly an important one, both in terms of load time and access time for the user. So it's a direct effect on UX, right? The fact that I can go in and access my scripts immediately that are currently local, right? These, if I click on these actually come down. These actually come down from the back end. Like I click on this, it's downloading now. No, it came down pretty quick. I could ostensibly have an app that doesn't present it to me until it actually retrieves it from the back end. But it's a lot more chatter with the back end, so it's more network cost, both in terms of the service and also for the user, right? The users, depending on their plan and their data plan, not as much of a big deal these days, but there's a network cost. And that doesn't even deal with the fact that if they go offline, we have an offline feature. In fact, I think if I turn off my Wi-Fi, let's do that. It's not affecting, oh, that's because I'm on a wired connection. Yeah, it's funny, I had Wi-Fi on, but I actually have a direct line to my router. Okay, there we go, I just unplugged. So you can see we have the offline feature here. So I'm offline. Now, it still keeps me logged in, which means I have secured access to my account. If I log out at this point, I'm basically securing my account, which is an important feature. I'm gonna stay logged in. But I can still access the script. So I can still get this guy. I've got breakpoints here. So these are all the breakpoints I set for line set, which I talked about in the first video. There's our script, all right? And I'm offline. So this is an important feature. Now I can't get something that hasn't been brought down yet, right? But I could be on stage, I could be behind, backstage, reading my script, working on my lines, and I don't need to be connected. If I reconnect, which I'm going to reconnect and plug in right now. So now I've got network connection. Should have network connection. Let's see. Do I have a network connection? Oh, there it is. Okay. So it reconnected us. Stay logged in. So yeah, there we go. So now I can pull down another script. I've got all these breakpoints. I'm going to have to re-enable them. I'm going to say no. Yeah, okay, that's fine. Anyway, this is the script. And there you can see I've got some comments in here. Now the line sets I've disabled, right? So these are going to be blank. There's going to be no line sets, even though there are line sets recorded, because that's part of this process. So anyway, what's my point? Reducing complexity. This is a perfect opportunity to do that. This is a perfect opportunity to say, not only do I not need to add SQLite, not only do I not need to add Kotlin versions of these objects and the automatic conversion to Objective-C that has to be interfaced that would go along with that, but this information has been retrieved from the back end as JSON. When it gets created, when a new script gets added, it could be created as JSON because it's going to be sent to the back end as JSON to be persisted. So it has to be in a JSON, it has to be represented by JSON at some point. I mean, it has to. That's a given. That's the one representation that we can't throw out. But maybe we don't need these others. So we don't need core data. We don't need the abstraction that it provides, unless we decide to take the JSON and store it in the database. But what's the point of that? What am I going to have, a table that basically just says, JSON string? Have a table called JSON. What's gained by that? Maybe easy enough just to store them as flat files. Could be a question of access speed, but that's something that can be performance measured. It can be measured, and then it can be tuned. So the straightforward approach would be, because again, the scripts themselves, all of these scripts are PDFs that are already stored as files. The videos are already stored as files. It's already using local file storage to keep all this information anyway. So storing something else as a file is actually less complexity than having a whole nother mechanism of persistence that's really not needed. So not only am I not going to add complexity taking this approach by adding these other new pieces of technology, but ultimately when I rewrite, when this is replaced with, this is going to be written as Kotlin code dealing with the JSON, retrieving it from the back end, sending it to the back end, and then storing it as a local file, will replace the core data, right? This is getting, I'm replacing this, and this is going to be the experiment. I'm replacing this right now. This is now dead code. So this core data will go away. So again, removing yet another layer of specific technology, core data, its API, its particular nuances and ways it works. We can get rid of that. So I think this is a big win. The only potential vulnerability I see here is a performance one. Again, I'm going to do this incrementally. I'm going to start with this class. We can very quickly measure the performance, do some stress testing, do some load testing on it, and see, does this need to be optimized? Do we even need an in-memory, do we even need a structural object representation of this? Can a line set be just held as JSON and used as JSON? Again, it's just metadata. It's metadata for the real stuff here. And the real stuff, if we looked at a line set, is an audio file, right? The metadata is the name of it, right? I mean, you're looking at it right here. Here's the displayed name, when it was modified, when it was created. But the reality is, I think the lines here, this actually points to audio files. These are audio files. It's metadata for audio files. It's multimedia. This is a multimedia app. So the metadata is the trivial part of the persistence. It's critical, it's important, but it's not significant from certainly from a performance standpoint, from a storage standpoint. So I'm convincing myself here, obviously, but I think this is a good revelation and it's a good win. And not only do we avoid adding new complexity by taking this approach, we can even subtract complexity that already exists in the existing app. And I like the sound of that. So rather than beginning the work there, that makes the second video basically a monologue. And if anybody listens to it, great. If they don't, that's great too, because this is really just me thinking out loud here. So to myself and to you and all your adventures in programming, I wish you the best of luck.